So maybe I'm the first one to give a blackboard talk. So also for that, there will not be many drawings. Or I will try to be maybe more conceptual, not give too much details. And we've learned the importance of having bridges. In fact, what I want to talk today is an example where you not only have one bridge, but you have several, and it helps you solve a problem. So maybe you can think of that as a prisma. You send some light, and then you have lights of many different colors. So the key thing I want to talk about will involve monotone Hurwitz numbers. So Hurwitz numbers, usually they're numbers of coverings, branch covers of the Riemann sphere. But you can reformulate everything in terms of permutations, which I will do. So I will fix lambda and mu to be two permutations of an integer d. And so SD for notation will be the symmetric group in D element. And the monotone Hurwitz number, so that will be strictly monotone to start with, depends on two partitions of D. And for me, it will be a generating series with a formal parameter h bar and a symmetry factor. And then what you want to do is to count the number of ways of factorizing the identity in the symmetric group. So you write sigma naught tau 1 tau k sigma infinity equal the identity. You want sigma naught, so everything is a permutation in element in SD. Sigma naught should be of type lambda. So lambda is you can represent it like a Young diagram. And the length of the rows are telling you what are the lengths of cycles in a permutation. So that's what I mean by type. Sigma infinity should be of type mu. The taus must be transpositions. And we want the strict monotone condition, which means that it's a transposition of two elements, AI, BI. I can always say that BI is bigger than AI. And I want the BIs to strictly increase. So what I write as max of tau 1 is greater than max of tau 2, and so on, bigger than max tau k. So it's a nice collection of numbers which have been very much studied. And you can also consider the weakly monotone version. In that case, here I want only a weakly order. And for convenience here, I'm putting a minus sign in that case. So now is the trick. One has to push on this button. Yes. Great. Okay. So now I want to talk about partition functions. So we always say partition function to mean some generating series. Here actually it will encode exactly a function on the set of partitions. So I'm going to call a topological partition function any formal series of the following form. So it must be an exponential. There's a formal parameter h bar with power 2g minus 2. So g are non-negative integers. And here you're going to sum over all lambda which are so Young diagrams, again partitions. And here there are some coefficients, arbitrary. And I will put p lambda 1, p lambda l. So that's up to the length. I will add something later. And I want to see that as an element of lambda, the ring of symmetric functions in countably many variables. And so it's well known that this is the free ring generated by P1, P2, etc., which you can think of as the power sums. Except that here, maybe I have to complete a little because I'm considering formal power series and I put an extra h bar. So these numbers are arbitrary, and just for convenience here I'm normalizing by z lambda, which is a symmetry factor, the product of the length of the rows and the product of mj lambda, where this is the number of rows of length j in my partition. Factorial. Good. So when I have this kind of thing, I can also, if I want to expand the exponential and collect the various terms, so you gotta have 1 plus a sum over Young diagrams. And I want to give a name to the coefficients. So here I will have, again, that's what I will call p lambda. And here I will call m lambda the coefficients. And I want to normalize things where I put a certain global negative power of h bar in front. This is the total number of boxes, so that's d. And that's the length of lambda, the number of rows. So this m lambda, it's really a function on the set of partition 2. A priori it could be formal power series in positive and negative powers of h bar. Good. So what we want to consider, and I'm going to write it aside because I want to keep it all the talk long. It's a situation where we're given two topological partition functions. So z and z check that satisfy a master relation, which is, so each of the z and the d check have their function on partitions m and m check. And m lambda is given by, so you can think of it as an infinite column vector indexed by partitions. And I'm going to multiply by a matrix to go from the m check to the m's. And this matrix is up to a symmetry factor going to be given by the monotone double Hurwitz numbers. So I want to consider a situation where I have two collection of numbers given, and I mean packaged in such a function, but they are related in this way. In fact, one can prove that if you have the relation this way, it's easy to invert it. And the inversion goes by, instead of taking strictly monotone, you have to look at weakly monotone. So when you invert, you need to have some signs, and this is why I had put my sign in defining the weakly monotone. And here I don't have the chapter. And lambda is the argument on the left-hand side. Thank you. Okay. In the rest of the talk, in the second part, I will give various situations where this is the case. But first, I want to describe, what is the result about this? So in these situations, for the moment, you have to believe me. In general, one wants to extract a bit more refined information, for example, G by G. You can already think that G is like a genus in a counting problem. So in order to do that, you just encode this partition function in a different way. So in generating series that I will call correlators, which are indexed by G and N. And so if you're given a Z, you want to consider G, big G, Gn. That will be a generating series in some variables, big X1, etc., big Xn. And it's going to store information about these fg lambda when the partition has length n exactly. So you do sum over L1, Ln, positive, fg. So let me write lambda L. That means this is just a sequence, unordered sequence of positive integers. You just put them in order to form a Young diagram, to form a partition. That's lambda L. And then you put x1, L1, xn, Ln. And it's just a little convention that perhaps I should write my G below. In the case of G equals 0, N equals 1, which would later correspond to look at disks, if you have a counting problem, I want to put an extra 1 here. So the question is, if Z and Z check satisfy the master relation, what is the corresponding relation between G, Gn and G, Gn check? And typically, it can be more efficient because here, as you do generating series, you encode all partitions of length n at once. So in Hurwitz theory, or to count map, that's typically what you want to do. Okay. So the main result is about of this work is about such a formula relating the two, a functional explicit functional relation between those two things. So what can I do? Maybe here. So the main result. So this is in all what I'm saying is a joint work with Séverin Charbonnier, Elba Garcia Failde, Felix Leid, and Sergei Shadrin. And so it's in a work that it's on the archive since maybe 2 weeks. So the result takes this form. Introduce a change of variable. So big X, you're going to write it as W divided by G01 check W. This starts with 1. So X looks like W when W goes to 0. So you need it's a well-defined change of formal variables near 0. Then G01X, upon this substitution, is going to be G01 check of W. G02, in fact, you have a formula that you've already seen in some form in Elba's talk. So you add to it this double pole. Then you take two copies of the variable w, one for x1, one for x2. Here you will have d log w1, d log x1, d log w2, d log x2, multiplied by G02 check w1, w2, plus the double pole, but now in w's. It's not a fraction, everything is you sum the two terms. So I will try to explain a bit later that this relation here is not new. It's essentially Voiculescu R transform in free probability. This formula is come from the work of Collins, Mingo, Schniadi, and Speicher. So this formula, as I will say later, relates cumulants and free cumulants. And these authors, about 15 years ago, have defined higher order free cumulants. And they could prove for order 2 this functional relation. And part of the theorem, we retrieve this by a slightly different method. However, yes?
This encodes all orders?
This is order 1, this is order 2. So the problem that was posed here, they have defined higher order free cumulants for any n, which would correspond to G0n. But they left an open problem to find the functional relations generalizing this. It was not possible to get it from they defined this thing by combinatorics of objects called partition permutations, and they could not really make generating series relation out of that. And we answer this problem. So G0n so it's a sum over R1, Rn non-negative. Here there's some operators depending on Ri involving a variable Wi, which is obtained from xi by this change of variable. So we first write the formula and then explain a bit the different parts. Then here you have a sum over some trees. And you're going to have the product of all I over it of G check 0 cardinality of I Wi. So that's the structure of the formula. Here, this is an explicit differential operator of order Ri minus 1. And so what I forgot here to write the product over I from 1 to n. And I'm going to spare you the expression, but it's an explicit one. What is the set T of trees? So these are bicolored trees. I'm going to write to give some examples now. So how does it work here to erase? Do we have this? Ah, that's wonderful. There's a third board. Oh, even better. So bicolored trees, I'm going to say what happens for n equal 2, for n equal 3. So you have vertices which are red and vertices which are blue. It's bicolored, so red can only be connected to blue. So that's the only one there will be for n equal 2. And for n equals 3, I have that. So the blue ones are going to be labeled by 1 to n. And here I can have something like that. Or something like this. And one here is a central guy. You have two more trees where you put 2 or 3 here. These trees are abstract trees, they're not planar. So the rule is that the red vertices are labeled. No, in my picture, they're the ones which are not labeled. They have valency. The only rule that they have valency bigger than 2. And the blue, they're labeled from 1 to n. And that's all. Except that I have my R. And what is R is the valency. Ri plus 1 for the ith one. So if you fix n, you only are going to have finitely many terms here that can contribute. So it's an effective functional relation. So now I have to explain this. Is the product over, so what is I? I look at each black vertex and at all the blue vertices which are connected to that one. This is I. So you can think of it as a hyperedge. So I, it's a subset of edges or of blue vertices connected to the same red one. So in that case, I would have exactly 2 i's, the one with 1, 2, and the one with 1, 3. Okay, so what we learn is that for each blue vertex, the labeled one, there's a differential operator. And the weight of these hyper edges, so it's somehow the weight for the black vertex connected to, depends of what you see here. You're going to put, there's a W for each blue vertex. There are the label guys. There's W1, W2, W3. And when I see something like that, I put them together in a G03, W1, W2, W3. And it's a G03 check. There's a little modification, the last thing. That product prime means replace G02 check. It's a tree, so these two variables are different by adding a double pole. So you may be worried that, well, this is not anymore a formal power series in the n variables. Well, it is if you give an order in the variables. You first expand W1 near 0, W2 near 0. And the little miracle of this formula that this thing, which was a natural formal series independently of the order in which you expand, actually all the negative powers disappear. It's not easy to see from the formula, but it's part of the consistency of the result. Okay. So this main result, in fact, there's a generalization to get GGN. Now the weights of these red vertices are a bit more complicated, and trees are replaced by genus G graphs. So essentially the differential operator I didn't give the expression of, which I said explicit. There are other differential operators, but longer to write. And then graphs of up to genus G, in fact. Okay. So somehow that's the answer. And what I need to do now is to motivate a bit the problem. And what does it give the answer to? But I was fearing if I was first giving the motivation, I would never have the time to actually write the answer, which would be a pity. So, I could have written actually the 0,3 case where the formula actually is quite explicit and nice, but maybe I prefer to give the motivations. So, I want to talk about maps. So we already know what is a map. And if you fix lambda, a partition of D, you can consider, so what I want as my function on partitions is going to be the generating series of Boltzmann map with that as encoding the boundary parameters. So I'm going to have a sum over maps. I'm putting an h bar to the minus the order characteristic. So somehow these are sorted by topology. There's of course the automorphism factor. And then you would have the product over all faces of some Boltzmann weight degree of the face. And I'm summing over possibly disconnected maps, because if you remember that was m were the coefficient of the exponential. So possibly disconnected maps with n rooted labeled boundaries of length lambda 1, lambda n, n being the length of the partition. And that's what I would call, so what we call map here, but what I want to call ordinary maps, to distinguish them from fully simple maps. So in Jeremy's talk, in Elba's talk, we've seen simple maps in Jeremy's talk, but he only had one face. He was looking at this or unicellular thing. When you have several faces, the condition of simplicity, it depends what you want to choose. Either you want that each boundary doesn't touch itself, or maybe this boundary cannot touch either this one. Depending what you choose, you have a different notion. So the fully simple mean that at each boundary vertex, there can be only one incoming boundary edge. So it means in particular, different boundaries cannot touch themselves. So fully simple means, so here you have a boundary. When I go around the boundary following an orientation, an arbitrary one, I'm going at some point to come at this boundary vertex, and then I'm going to exit. But then I cannot find another boundary vertex that's going to come again at this vertex. We define M check to be the same generating series, but now over fully simple maps. And the claim is that you have the master relation between the two. We know of two bijective ways to prove this master relation. And this was in a work with Séverin, Normando, and Elba. And I'm just going to check one idea of one of the bijective proofs. The idea is to simplify. To get to a fully simple map. What those can simplify mean? You look at the first root of the first boundary, and you go around the boundary starting from there. Maybe sometime, because you're in ordinary map, you may meet a vertex where the map is not fully simple. So you may be in a situation like this, where, so I write here in terms of ribbon graphs, arriving from here, so that's a H, and my boundary is here. But I have somewhere another boundary here. So this vertex is not fully simple. Maybe it could be the same boundary or a different boundary. So you can code maps by triples of permutation that tell you sigma 0, sigma 1, sigma 2. These are permutations on half edges. And sigma 0 tell you when you go anti-clockwise around a vertex. So I arrive here, I go anti-clockwise, which is the next one? Also incoming. Sigma 1 tells you what's the opposite oriented half edge. And sigma 2 is telling you when you go around the face anti-clockwise, what's the next one? Here it is here. When I'm in that situation, I have here an H prime. And my sigma 2, H prime is here. But there could also be other boundaries coming here, so there's other edges here coming to this vertex. What I want to do to simplify, I arrive here, and I want to go as far as possible turning in this direction so that I meet the last boundary, which exists because it was a vertex where I was not semi-simple. So here there's no Or maybe I did it in the other way. So here there should be no other boundary on that side. But here there could be others. We don't know. So I take the last one going in this direction. And the simplification means that, well, we want to actually make it simple. So don't have this here. So disconnect that in two vertices. Well, now the boundary is going to be in the middle. And well, of course, here you could still have stuff. But when you do that to a vertex, then you continue your exploration. Then you finish with the first boundary, you can go to the next boundary which has not been explored. So you go through all vertices and you simplify all of them. At the end, this is going to disappear. So the only thing that you did to pass from here to here is modify a bit these permutations. The phases are not the same. So what you do is that you define, you updated sigma 2, or first sigma naught, to be a transposition times sigma naught, and sigma 2 to be that transposition in this direction. And sigma 1 remain the same. And then the relation that is constitutive of maps is preserved. You could adjust the conjugation of the identity. So when you do that, exploring all the possible boundary vertices, you're going to update this thing by a product of transpositions. And because from the roots, you could actually define a full labeling 1, 2, 3, etc., up to the total perimeter of all the boundary faces, your transposition comes in a strictly monotone order. So you get something, well, I'm not going to write it here, but that's how appear the sequence of transposition, which is a factorization of the identity. And so this is essentially how it works for one proof. Okay. So next thing I want to talk about random matrices. So let's consider a matrix A, which is random. A random Hermitian matrix of size n. So it depends on n. And you want to consider one whose distribution is unitarily invariant. And so in such a matrix model, you want to understand what's the property of the statistics of the spectrum, of the eigenvalues. Because some of the eigenvectors are uniformly distributed because of this. So for this, you introduce some functions of which you want to compute the expectation value. So you can define m lambda, which is the expectation value of the product of traces of powers. And you can introduce another one, which is expectation value of now the product. So I'm going to fix gamma 1 gamma n is the length of the partition, some pairwise disjoint cycles. Of indices in 1n. And so you need to take n big enough compared to the size of lambda. And now instead of taking the trace, which is doing some cyclic product of entries of matrices, but summing over all indices in a cyclic order, you just want to take the product of entries in this cyclic order. So I from in the support of pi, and pi is the product of these cycles. So 1, etc., up to L1, I come back. Lambda 1 plus 1, etc., up to lambda 1 plus lambda 2, I come back to this lambda 1 plus 1, and so on. These two satisfy the master relation. This is a consequence of Weingarten calculus. And so what happened is that, let me call that product P lambda. Okay, so it's another funny notation for this product of matrix entries along these cycles. And this one is going to be little p a like this. So this, for all the partitions lambda, it's a basis of the polynomial function in the matrix entries, which are invariant under a unitary group by conjugation, because they only depend on the spectrum. Whereas this certainly is not unitary invariant, because you fixed these cycles. However, you have a matrix whose distribution is unitary invariant, so you should be able to project those ones onto those ones. So what you write is that P curly lambda A, you average over a unitary group that's the Haar measure. And then, so this is a polynomial in the entries of this matrix, so you have to compute some moments of a Haar distributed unitary matrix, and then there will be expectation value for the entries of A. If you do this, you obtain the relation between M check, because that's where I start, in terms of the weakly monotone Hurwitz numbers. Okay. So the question becomes more interesting when you don't consider only one matrix, but several matrices, which is what you do in what's called non-commutative probability or in operator algebra. So the situation that was considered by Voesculescu, which actually motivated the introduction of free probability, is a situation where now you have two such matrices, which are random and independent. And one of them is unitarily invariant in law. And then the question is, what can you do? Can you predict the statistical property of the spectrum of A plus B? And because A and B don't commute, it's not obvious. But what you can do in that situation, or in more generality, if you have two elements which are free in the sense of Voesculescu, which happens in this case, is you can say, okay, I have A, and imagine I already know the statistics of the spectrum for A, which is more or less the same as knowing all these moments. So you know M A lambda, and the same for B. Once I'm in that situation, it doesn't cost much to actually also assume that B has the same unitary invariance. So once I'm there, I can look at M check. So these observables. And it's really a bijective thing. They encode the same information but differently. Good. But now, there is actually some additivity property if you want M check of A plus B you can obtain it. So here I'm cheating a bit, because that would be, for the connected expectation value, that would be exact additivity, and here that's the disconnected. So up to taking the connected. So you have this. So now you can come back, since you know these two, you can come back to MA plus B. And you have all the information that you want. Of course, the problem is how to do that efficiently if you have a concrete matrix model. And this is why you actually want to have generating series formula. So what people have been more interested in free probability or operator algebra is the case of large random matrices. So you send n to infinity, and you assume that your laws behave well, so you have a limit distribution. So you assume that that's the expectation value of the trace of powers of just one, trace of a to the k. It's a trace, so there should be n eigenvalues, so it's k like n. You assume that these converge to something. Then one can prove that, well, this also exists. So if I want this thing to exist, there's a little normalization. Here you sum all indices. So you have a scaling of n. So here I actually need to scale that by n to the d because there is much less term here. So this is also going to converge. So let's call that F01L, F01 check L. You make generating series as I did before. And it's the result essentially of Voiculescu. That these two are related by the functional relation, which is still here. If you assume now that not only there is law of large number, but also covariance exists in larger limit, then you can speak of things with two rows. And in larger limit, you're going to get this formula. That's what Collins, Mingos, and Speicher did. If now you want to understand the whole topological expansion for these matrix models, you have to use these other formulas. How much time is remaining?
5 minutes.
Okay, perfect. So somehow that motivates the problem. And in order to prove these formulas, so I want to give, in fact, two other interpretations or settings in which these master relations appear. I think it is still here. And that will give us, that gives actually the key to prove these such results. What I may also add is that, so in particular, that applies to maps. And in fact, the simplification algorithm which I described, it doesn't depend at all what happens inside the map. So it also applies to maps where you can waive the condition that faces are disks. So it applies also to loop models, yellow faces which are disks and Silanders, or more general things which we call stuffed maps. So Ising model, pods, and so on. If you know how to enumerate fully simple maps, you know the G-check, then you know also how to connect, how to get formulas for the ordinary maps. And it's totally universal relation, doesn't depend on the model of maps. So you can take the result of Krikun, for example, which gives you G0 and check for all n, and put in this formula the question, do we get new formula for number of maps for triangulations? I don't know if this is new. So the two last perspectives, so it's Fock space. And in fact, the origin of the definition of this, you have to start from somewhere when you say it's related to free probability. So you start from the combinatorial definition of higher order free cumulants, which are given by these four authors. And so it has to do with partition permutations. So here I will just state, because I don't have the time to define these objects in detail, that if you allow something partition permutation with genus, which we call surfaced partition permutation, then you can actually define also higher genus, higher order free cumulants in a combinatorial way. And the way they obtain from cumulants is equivalent, and that's the key lemma somehow, to the master relation. So you could say of Gn free cumulants, G equals 0 corresponding to higher order free cumulants, is equivalent to the master relation once you encode them in a topological partition function. So on the Fock space, what I want to say that the ring of symmetric function in infinitely many variables as a vector space, it is also the sum of the centers of the symmetric group algebra. And essentially up to normalization here, the power sum elements go to from conjugacy classes element here. There's a normalization I don't specify here. So from this perspective, we know that here there's you can multiply, it's an algebra, and it's commutative because you take the center. So you can look at the Jussies-Murphy's elements, Jk, which is an element in here, which is a sum over I smaller than k. And I'm going to slightly simplify the discussion compared to what it is. So Jussies-Murphy don't belong to the center, because it depends on the ordering of 1 to d. However, what is known is that symmetric functions, if you take a symmetric polynomial in the Jussies-Murphy, and then you complete by zeros, that's a symmetric polynomial in countably many variable, that's in the center. So now I'm saying that the master relation between these functions on partitions, which are encoded into this topological partition function, which are elements in here, they're related by action of a simple operator, where D is the product of 1 plus h bar. The Jussies-Murphy, that means sum of h bar to the r, the elementary symmetric in the Jussies-Murphy. But if you think of what these Jussies-Murphy are, it's a sum of transposition up to here. So this guy, it's a sum of products of monotone sequence of transposition. Coming with an h bar to the r. So this is by no means new. I mean, these monotone Hurwitz numbers have been defined by Goulden, Jackson, Novak. And this type of relation appear very clearly, for example, in the work of Harnad and G paquet on weight Hurwitz numbers. And this point of view actually explains why I say you can invert easily the master relation. Because if you take the inverse of this operator, you get the complete symmetric, which is now, when you expand in this, it's the weakly monotone sequence. So the non-trivial thing happen if you just write z check as z check times 1. Here you have multiplication by p's with the coefficient which are the m check lambda. And you want to commute that with this operator here. Because these operators are going to act trivially on 1. And to do this, in fact, there's a lot of things known about actions on this ring. It dates back to the work of Okunkov, Panaripande. So you know how to compute explicitly these commutators that makes appear sums over graph. And the particular way to use it, there was a recent advance by Bishkov, Dunin-Bakovsky, Kazarian, and Shadrin, which really does that for you quite systematically. And that's what we use in this paper to obtain these functional relations. I will stop here. Thank you.